Tuesday you don't. There's a new procedure that, I should say an amended procedure that will show up in Canvas. So for Thursday, things will be a little bit different. And then the other thing, I'm going to say, hold off on the write-up because I haven't covered equilibrium, which is the concept you need in order to answer all the questions in the lab. And there's also some post-lab analysis stuff that's not included in the lab manual that, unless you have it, it's going to make actually doing the calculations kind of tough. So, procedure you can do tonight. They collected data. You're going to hold on to the data. I'll post in a further amended procedure lab sometime before the weekend. If I don't get this lab next week because I haven't covered equilibrium, I'm not going to stress about it. Okay. So, there you go. Just Thursday group, you're going to collect some data. We'll say that calling you. Amber, you want to give your spiel? Yeah.
Hey guys, I'm Amrit. Yes, most of you guys know me. I was the SI for Chem162 with Professor Davis, also 161. I see a couple of new faces in here. I am the new SI, well not the new SI, but I'm the SI for 163. And basically what's going to happen, well raise your hand if you guys know what SI is. Okay, so I think all you guys are familiar with it. So I'll be your SI and then I'm going to be hosting around 2 sessions, maybe 3, depending on availability of some people. And let me see, I got a couple of things I want to mention for the tutoring center as well. I know the past 2 quarters, there's been a lot of people come to SI sessions, so it's kind of hard to get that one-on-one basis for like students that need that extra help. So there's this thing at the tutoring center called peer-led study groups. Are you guys familiar with those, by any chance? So basically, you get a group of people who are both all in the same course and they need that extra help and need like a more closer, like 2 to 3 people group. And then I can host a session of peer-led study groups where if you need help on assignments, lab reports, and like more conceptual stuff, I could definitely do that. If you need something like that, you can come talk to me, like gather a couple people that might want to join up, and then we can set up a schedule like that. Let's see, so Chem 161, 162, I was really hands-on with this stuff, like helping people through everything. This quarter, I'm gonna be stepping back a little bit and letting you guys figure your own ways, because not a quitter, but the way it works is by now, if you guys are still relying on me, it's probably not good. So I'm gonna help you guys still, no worries. Like I'll get you through whatever problems you'll have, but I'm gonna be letting you guys take the wheel more, and then we're gonna I'm just gonna be answering questions. So we'll see how that goes this quarter. And then I gotta.
It'll be fine.
Yeah. So I got a remind app. You guys are familiar with the remind app? You guys know what that is? Okay, so if you guys are not familiar with it, if you get your phones out, and then that's a bad one. You guys get your phones out and then text this number here, 81010, and then you text spring 19CH. Can you guys see that okay?
All one word?
Yeah, all one word, no uppercase.
Spring 19 what?
CH. Double check that's, oh yeah, so there's an @ symbol in front of it actually.
In front of
The spring, yeah.
For those of you on Verizon, apparently Verizon is not supporting Remind as a free.
They fixed that.
Did they fix it?
Yeah, Verizon's good now, so yeah, and if you text this number, I'll be able to send you guys notifications about when the sessions are happening, if I need to cancel a session or something like that. So as of right now, starting, I guess, maybe this Thursday, I'll be starting the session. So the first one's probably going to be 4:30 to 5:30. I'll send a reminder just in case if that changes. But as for the second session, I need you guys to fill out these surveys real quick, and we can set up our session that works for supposed to be.
So guaranteed we have a session on Thursday.
Yeah, and if something changes, I'll send a message to the reminder. So I'll pass these out. Pass those on this way. I think I got enough here for everyone. And I highly recommend, if you guys are, if you have other questions that I might not be able to answer, the tutoring center is always open for drop-in. So if you guys need the extra questions, like 5-10 minutes with someone who's an expert in chemistry, stop by the tutoring center and they'll be able to help you over there. So real quick, I also am taking classes this quarter, so my availability in the morning, I have class from noon to 1. But if you need to email me or send me a message through the Remind app, I'll be able to answer those. That's fine. You can message me through Canvas as well. I'm in the course as well. I think there's one other thing I need to mention. No, I think that was it. Any questions about the SI stuff? I think most of you guys are familiar with it, so you should be good. Right? All right, cool. If you guys have any questions, you can just come up to me at the end of class or whenever you get the chance. Thank you.
And if you haven't done so, check Canvas.
Right now?
Well, if you haven't checked it in the last couple of days. There's a 3-question, I titled it like it, but it's 3 questions to deal with topics from last week and then tonight. So in order to answer the 2 questions for tonight, you kind of had to look ahead a little bit. Everyone who's done it so far is 100%. They're not difficult. They're really just I'm trying to force you to look ahead a little bit in the material. So tonight, the one for today, they've got here to do at 9, so at 9 o'clock it'll close. Make sure you, if you haven't done it. I'll probably put one in for Thursday as well. Okay. Okay, the first bit about tonight is all about rate laws, what they mean, how to figure them out, what to do with them, what kind of calculations you're going to make. I've got a practice thing here that I'm going to have you do in a little bit, just to see what kind of questions you might have about how rate laws work and what you're doing. Okay. Generally speaking, they look like this. And the K that you see, this should all be in here. The K is called the rate constant. Sample reaction looks like that. So A plus B goes to C. And it doesn't matter what the reaction is. If you're writing the rate law for this expression, that's what you saw up on the screen. It's got the K times the concentration of B, or A raised to some power, times the concentration of B raised to some power. Okay. That's what the rate law is going to look like for any given reaction, where you are looking at the reactants. Okay. So that's the reaction that shows up here. The rate constant is the thing that lets you deal with the concentrations here in the time. Because you'll remember rates measured in like molarity per second or molarity per minute or some kind of a change in amount per minute. There's no minutes that show up over here on the right-hand side, at least with respect to the 2 terms A and B. The rate constant lets you deal with the time factor as well as whatever shows up for concentration. You'll see a couple of examples of that here. Then, this one. When the concentrations of things are changed, so that's like in the lab you did for the Thursday group, the lab you did, you manipulated concentrations, you should have seen that it took less time or more time for the reaction to occur. The manipulation of concentration will change the rate, and the exponents that show up here will let you figure out how, okay, and to what extent. I'll walk you through this as well, have you do a sample problem or two with it. These are called the order, and these are also for you going to be small whole numbers. You're looking at like 1s and 2s. Okay. Maybe a 3 showing up in terms of calculation. And then finally, if you add all of the orders up, so if it was say 1 and 1, the overall order would be 2. If it was 2 and 2, the overall order would be 4. Okay. That's what the rate laws look like. And like I said, the next bunch of slides and calculations are all about how to use this, how to figure out what the M is, how to figure out the N, determining the value of K as well as the units that go with it. All right. Any questions about that stuff? Next. Oh, last bullet. Sorry about that. There is no way for you to figure out M and N without looking at experimental data. So you'll have to, as you'll see a couple slides down, there's a data table that's got how rate changes with changes in concentration. You will figure out the values based on that data, and then you'll use all of that to actually figure out the value in the units per K. Okay. Then, units. All right. So for the rate constant, I'm going to go back to the doc reader in just a minute. The time units that you look, or excuse me, the time units can be seconds or minutes or whatever. It's some sort of a time. Concentration, number one, most of the time you'll see it in molarity, but remember that pressure and molarity are related, or pressure and concentration are related. If you increase the amount of gas in the system, you increase the pressure. If you reduce the amount of gas, you reduce the pressure. It's analogous to concentration and molarity. So you can have pressure measurements representing concentration, treat it the same way. The rate constant, that's what we go to next, have to allow for that. So
you said pressure and molarity?
They're analogous. So like if you have a closed system, a closed container, if you keep increasing the amount of gas in there, you increase the concentration of the gas, but you're also increasing the pressure. Increase the moles of gas, increase the pressure. If you, on the flip side, decrease the number of moles of gas, you decrease the pressure. Okay. So, let's go here. All right. When you're determining the rate constant, whatever number happens to show up, if you want your rate to be in molarity per second, for instance, in this case, just cover this up. That has to equal something times the concentration. And if the concentration is molarity, here's a simple question. What do the units for the rate constant have to be?
Molarity per second.
Is there anything that goes on the top?
No.
No. The two sides need to be identical in terms of their units. So the units for this rate constant would just be seconds. So if you were to report K equals, you'd have a number, and it's written as seconds to the negative 1, which means it's whatever over seconds. Questions about that? let's go to the second one. If in this case you want the rate to be molarity per second, you need to know the units for the rate constant K, but A and B, I'm just going to say that exponents are 1 in this case to make it real easy. Concentration here and concentration here. What do the units for the rate constant have to be? To make it this. So I've got 2 molarities here, but you don't want 2 of them in the answer. You only want 1. So you've got seconds times molarity on the bottom. In that case, when you do the math, one of the molarities would cancel. If you were to report the value for K, it's going to equal some number, and then it's written molarity -1, seconds -1. Okay. That's because if you want the math here, whatever numbers show up, to result in molarity per second, you need to get rid of one of the molarities. So you're left with 1, and you're left with seconds in the bottom. How about if you have what are the units for that one? So 1 over molarity squared seconds. Because this is going to be molarity squared times molarity. And you want to make sure that 2 of those molarities disappear so that you have seconds on the bottom, molarity on top. So this would cancel, and you've got molarity on top, seconds on bottom. Okay. What questions do you have about this? I'm not even worried about numbers. All I want you to see is that you've got to pay attention to the rate units and then how the right side of the equation behaves. If you've got just 1 concentration unit or term here, then K is simply seconds to the -1. If you've got 3 molarities, you cancel 2. Questions, concerns? Okay, so let's go here. All right, so the next part is figuring out the order. So like in that M and N, what are the, how do you figure out the values? So what do they mean? Show you how this works. Okay. Okay, go to the doc read. Here's the idea. You've got an expression that says something like this. Okay. So the rate's equal to K times the concentration of A raised to some power. And let me label this 1, and then I'm going to label this one 2. And I double the concentration of A, and I'm still interested in what this exponent is. And if you know that rate 1 is equal to rate 2, and remember that K is constant. Okay. Here's your question. If K is a constant, and these 2 rates are the same, even when you double that concentration of A, What is the value of M? 0. Okay. If it's a 1, so you can mental math this. If you put a 1 here and you put a 2 here, what does that do for the value of the rate? There's a 2 there. It doubles it. Okay. But you're saying, at least in this case, I'm telling you that the concentration of A is of no consequence for the rate. That you can triple the concentration and then the rates are still the same. You can quadruple it. You can put 10 times in there and the rates are still the same. As long as there's some A, the reaction occurs. Okay. Since the concentration doesn't have any impact on the rate, in this case, M equals 0. So, if you write the expression, you would get rate equals K times the concentration of A to the 0 power. What would rate be? K. And if that's the case, what do the units have to be for K?
Molarity per second.
It's got to be molarity per second. Okay. What questions do you have about this one?
So the concentration has no effect on rate.
Right. So Thursday group, think about your lab last week. You changed the concentrations in the lab. Did the time it took for the reaction to occur change? Yes. Okay. If the concentration had no impact, meaning you doubled the concentration, tripled it, or whatever, it would take, and there was no impact, you would see it take the same amount of time every trial. And all 6 trials, you'd see the same time show up. Okay. But since every time you change the concentration, the rate changes, in other words, the time it takes for the reaction to occur, that tells you that the concentration impacts the rate in some way. Part of the lab is figuring that out. So, in terms of like the question, this is what I'm going to have you do here in 2 minutes. This problem, okay? So you're going to have to do some stuff with it. And you'll need to understand how the rate behaves when concentrations are changed in order to answer questions like, what is the order with respect to A? Or what is the order with respect to B? And if changing the concentration has no impact on the rate, then the order is 0. Okay? Because if you change, like if you double this and there was a 1 there, then it would double the rate. If you doubled it and there was a 2 there, what would do the rate? Quadruples. If you get doubling squared, it gives you a 4. So it multiplies the rate by 4. So you're going to look at how does the rate change as you change the concentration. That's part of this problem. Yeah, Victoria.
So this is just when we're just looking at order versus continuously. That was just like a general rule.
Yeah, so last Thursday was just, here's rate as change in concentration, really just change molarity per minute or change molarity per second. And you're looking at all those examples where here's a concentration at time 0, concentration at time whatever, and you find the change and then divide by the time and you get your rate. Okay? So problems like this one, you have a rate given to you and you got concentration differences. This is more similar to what you did in lab, or what Thursday group did in lab. Okay. All right, so let me go back to here. Is that okay, at least for now? Okay, so let's go to conditions here.
shock reader.
Okay, so the idea is this. There's the expression for the rate law, whatever, and it doesn't matter what it is. Raises some power m, that's your order. In the second condition, you double the concentration of A, you're still raising it to some power that you're trying to figure out. If rate 2 is equal to twice rate 1, and you're doubling it, what's the value of m? 1. 1. Okay. If you triple it, and it's a 1, and I tell you that rate 3 is 3 times rate 1, the value of m is 1. Okay. So that when it tells you proportional change, if you double it and it doubles the rate, if you triple it and it triples the rate, that's your proportional rate, or proportional change. So in this case, m would equal 1. Okay. Any questions about that one?
I'm just curious what K is.
Why K is,
Not.
oh, for this part here? Oh, this, because like if you did the math, calculated that, and then you did the math and calculated that one, I'm asking how do those two numbers compare? So, I don't know, let's just say for the sake of argument that this equals 10 and then this equals 20. So this would be 20 equals 2 times 10. That's all that is. If you do, and that's if you do the math. So down here it'd be 30 and 10. Okay. All right. Other questions about this one? All right, the last one. All right, so what's the value of m for that one? Here, quietly. Square for 2, right? It's a square. Because if you double it and you get a 4 times the rate, m has to equal 2. If you triple it and you get a 9 times the rate, m equals 2. Okay, so m equals 2 in this case. This one would be for the first one. You would say this is first order in A. Excuse me. For the bottom one, you would say that it's second order in A. Okay. Questions about the bottom one? Anybody have a question you don't quite know what to ask? Or how to? Sure.
So how would we see questions like this from tests and viewers? What would
So
you
to get it, and like I said, I'm going to have you work through this one here in a couple minutes. I need to give you the how do you deal with a set of data to answer the rate law and the orders, and then how to figure out the K, and then make a set calculation. But this would be a question that you could see for rate, okay. Where you'd be given the equation, would be given a set of data, and asked to do something with it. Very typically, they are write the rate laws, calculate or determine value of K, figure out the rate based on some new concentrations. But you have to know how to manipulate that data set. So that's what I'm getting to next. Okay? All right, so let's go to this. Do you want me to leave these two up here for a minute?
Yes. Yes.
All right, I'll leave that there. So the proportional rate change, that's where if you double it in a double concentration, double rate, first order. Triple concentration, triple rate, first order. Quadruple concentration, quadruple rate, first order. The value of that exponent is 1. Can I flip it?
Sure.
Okay. Third condition, this is for a second order. That's the last example that you saw up here. Then if you double increase by 4, second order, it's a square. Triple it increase by 9, that's the square again. Okay. Looking ahead. President. Question?
No.
Can I move it ahead?
No.
Not yet? Okay. Alright, so these are just, like I say, behaviors, how things change, things that you'll need to consider in answering questions like a ship. And ready? Almost. All right, this is called the method of initial rate, and the data set on the next slide looks like this. Okay. Here's how you deal with it. And I'm only going to be interested in, for the next slide, the value of M and the value of N. Okay. And then this is kind of Jared's question from a minute ago. When you're looking at the kind of question that'll show up on a test or quiz or whatever, this addresses that. Okay. I'll ask you, given a data set, to figure out the value of M, the value of N, figure out the value of K, plus the units that go with K, and then perhaps ask you to do things with how does the rate change as you then manipulate concentrations. Can I go to the next slide? Okay. On the next slide, this is like you look at this, you're like, what the heck do you do with it, right? As you look at each of these data sets, like trial 1 to trial 2, you'll notice that the concentration of ammonium is doubled. Does the rate change? It doubles, okay? This was pretty easy to see, and then based on what you saw a minute ago, you're looking at a rate law like that, looking at just the ammonium, there's the M. If you see a double concentration doubles the rate, what's the value for the M? It's a 1. Okay, easy enough to see. If you look through all of these trials, then that tells you the answer for the ammonium. Now you want to look at the NO2. These are all the same. You can go to any one of these down here. So NH4 is held constant. NO2 is doubled here, or you could look at here to here as a triple, or here to here as a quadruple, or you can go double from 6 to 8. Look at 5 and 6. If you double the concentration, what happens to the rate? So the value for N is 1, right? Okay. Easy to see on a problem like this one. However, it won't always be quite as easy to see. Here's how you really do it.
Can you repeat that again?
Right, I will. I'm going to go to the next, or doc figure here in a minute. Okay. So, if you're just looking at how the numbers behave, this one is held constant. So basically it says this, the same amount is dead, there's no impact on the rate because of this, because the amount doesn't change. You change the amount of ammonium, so you double it. How does the rate change?
It doubles.
It doubles. And if you know the rate law is this, so you put a 2 there, you double it, and then the rate doubles. What's that number? 1. Right. Yeah. Okay. The same thing if you look at the other trials. If you take NO2 and you double it, and the rate doubles, then the value of N is 1. Okay. Here's what I want you to do. This is called the method of initial rates. This will work to let you calculate the values of M and N for any set of data, especially if you can't see the doubling or the tripling or whatever the case may be. There's an example in the book that I think gives you a 2.25 change, which is a little bit cumbersome, okay? You're going to do this. You're going to take a look at 2 different trials and compare them. And I've got up here on the screen, rate 2 to rate 1. The K is the same, and I'm looking at the concentration of ammonium raised to some power M over the concentration of ammonium raised to some power M times NO2 to some power N divided by NO2 to some power N. Okay. Again, this is called the method of initial rates. Here's what you're looking at. There's the rate expression, and you're trying to figure out M and N. From the previous slide or on the PowerPoint, I think you all saw that it's 1s. Okay. But if it's not so obvious, this is how you determine it. I'll look at one rate expression, there's for the rate 2. Now look at the other one, there's rate 1. The reason I put rate 2 on top is that, remember, rate 2 is a larger number, rate 1 is a smaller number. But lets me keep numbers greater than 1. Some of you would be able to have numbers less than 1 and do the same thing, but numbers greater than 1 tend to be easier for people to manipulate with pens. Okay? Do you have this on your paper? Okay. I'm going to go back to the other one. I want you to fill in the blank, or fill in the rate. This one, fill in here, and fill in numbers there. Okay. So fill in the rates, fill in the concentration for ammonium, fill in the concentration for the nitrate.
We can choose any numbers on the table.
Use rate the second trial and the first trial. The second trial on top, first trial on bottom. Okay. So do that. Fill in the numbers. I'll write them in up here. doc reader yet? Not yet. Okay. So here's what I've got. For rate 2, there's the rate, the K you don't know yet. You know the value of ammonium, the value of nitrite, raised to the powers n and n. And then I look at rate 1, there's the rate, K you don't know, concentration, n and n. Okay. Now, math-wise, what cancels?
Okay.
K's go away, they're the same. What about these over here? Right? Because it's the same thing. If you simplify what's left, and I'm going to dump all the units at this point, that simplifies to what? 2 equals, and this is 2 to the m. What's the value of m? This is called method of initial rates. So you'll have a data set where you can pick 2 trials. Do the larger numbers divided by the smaller numbers. It just makes it easier. If you inverted this, it would work as well. But having numbers like 2s instead of halves make it easy. Write 1 trial, write the second trial, cancel the things that cancel. And that lets you see very easily 2 is equal to the what? And the answer is 1. Okay. What questions do you have about this?
Is that a minus sign?
Yeah. For those of you who are new, are you good with the E notation?
Oh, okay.
Okay. Yeah. Some instructors don't use E. Some instructors don't like it.
I'm saying.
Yeah. So yeah, that's times 10 to the negative.
Okay.
Okay. All right. You can do the same thing for, say, trials 6 over 5. And if you look at 6 over 5, 0.404 over 0.0202, that would divide to give you a 2, right? So 2 to the n equals, and then 21.6 divided by 10.8 is 2. It would look exactly like that one, and you'd end up with 1. Okay. Any question about initial rates method? Is it reasonable? Look.
I was watching a video and he was saying that K was like, I can talk to you later.
Okay. If you find it, go ahead and ask. Yeah, Angela.
So we don't use it for experiments like 7 and 8?
You could. You'd end up with whatever 0.0808 divided by 0.0606 is. Was that 3/4 or 1 and I don't know whatever that is. 1 and a
Or you
third.
just round for the I guess what I'm asking is if you're not giving
You for this one, for these kinds of problems, you'll be given initial rates. You would have a set of data that would look like this, and then you get, it's like in answer, if you're comparing, say, 8 to 7, this is what, I'm not going to write all that out because everything counts except for the concentrations in that number. On the left, so you end up with that. then this is why I say it's not as easy to see if you're looking at, say, 7 and 8. Because, I mean, you'd have to know how to divide this and give 1.3 and divide that and give 1.3. But if you set it up like this, you can easily see what the value for n has to be 1. So, that's why I say the method will work regardless of what data you've got. And then if you get numbers that are weird that you can't easily see, are you good with doing things like that? Using logarithms to solve those? That's a bit of sheet snow. Okay.
Just so people
Yeah.
see.
Yeah, this the logarithm method. I don't know that y'all are taught logarithms well enough in math classes to use stuff out like that. Anyone's even shaking his head. So, Molly.
Up there we have 0.100. Is that, did you just forget a 0 in there, or did it?
Yeah. Thank you.
Okay. I stepped out for a second, so I didn't know if there was like a special math that
The funny
you
thing is
did.
about this particular problem, when I run through it, inevitably, I forget one of these 2 zeros every dang time. And then somebody always asks, and I'm like, oh yeah. So there's supposed to be a 0 there. Yeah.
Okay.
But every year, I did that with my AP kids running through the same stuff a month or so ago. Someone asked me, I said, is there supposed to be a 0 there? Yeah.
Well, I said maybe I missed something. Like the other numbers
No,
all lined up.
I
But...
forgot a 0. All right. Elizabeth, yeah.
So I found it, so
Okay.
to discover like the unit of K, a constant, so they're saying use like K equals M and then 1 to the N for like the order, like N would be like the overall order.
Yeah, so let's go back to here. I think we got, yeah.
And then T to the N.
Okay. So let me get a fresh piece of paper. We'll go here. At this point, you could write a rate law that says rate is equal to K times NH4 to the 1 and NO2 to the 1. So it would look like that. Okay. The next step that I'd ask you is determine K. Okay, so figure out the rate constant. You got, let's just show that data right there. Could you use that data to figure out K?
Yeah.
Okay, so am I all right if I just flip this all around and say K is equal to rate divided by concentration of NH4 to the 1, NO2 to the 1? Okay. And then you can plug in the numbers and say 10.8 times 10 to the negative 7 molarity per second divided by okay. What things cancel? One of the molarities, right? So you got one molarity here, it will cancel that one right there. You've got molarity in the numerator of a complex fraction. So when you solve this, where does that molarity end up? Denominator of the answer. Remember your complex fractions?
In the same day as logarithms.
So you get molarity per second over molarity over 1. To solve that, remember you take the reciprocal of the bottom multiplied by the top. I don't know what that rule is, but it turns into molarity per second times 1 over molarity. That's the way you solve that complex fraction. I don't know what the rule is called. Okay. So, somebody with speedy calculator fingers, what's the value for K? Did you figure it out? 2.7 times 10 to the negative 4? Okay, I think that's right. And the units that you end up with are molarity to the negative 1 and seconds to the negative 1. Okay. And that's because you've got seconds here in the denominator, and you've got the molarity here in the basically the denominator again. So that's your value for K for this particular reaction using that data set. If you solve it using the second data set, you will get the same answer. What questions do you have about this?
So that's like based off the second order? It's like the
So-
together, that's how you get the root, like
So the overall order for this one would be two.
two, yeah.
Right. Individual orders, this would be first order in ammonium, first order in nitrite, but the overall order is two. So if you look at the overall order for two, K has to have the units molarity in any point section. That's the only way to make it work out so that your rate would be molarity per second. Okay.
Is there any reason that it's written down as K over K instead of just K? Or any other way?
The only reason I did that is because when you look at a rate
Just
law
make
for
it-
any data set, that's what
Okay.
it is. So I'm including all of the rate terms for each one of these.
What's the most complex way you'd ask this question on a test?
Like that.
Okay.
Here's this data set, figure out the order, figure out the value for K and the units that go with it. And
Will
then-
we ever have to fill in the data set also?
No.
Okay.
If you had the value for K and you had the rate, you could solve for at least one of the concentration terms. Or if it was if all it was that first, if it was just first order in ammonium and that was it, and you had rate and K, you could figure out the concentration for ammonium based on that. Nick?
Maybe I'm reading too much into the data table, but if you go back to it, you said M is going to be equal to 1, whereas N is going to be equal to 1.33, correct?
Oh, no, dude. So, this one, Angela was asking what happens if you took, say, trial 7 and 8.
Well, yeah, because it's reversed if you take 3 and 4, where M is equal to 1.33, and then N is equal to
3 and 4, so for 3 and 4 you get.
And if you were to give us a question like a data table like this on a quiz, and we just use 2 sets, we got different numbers.
Hang on. Show you again.
I mean, I guess does that make sense what I'm asking?
Yes, but so here's I flipped these ones. This one is going to be 1.33, the n equals, and then this thing is going to be 1.33 as well. So it's not that the n or the m is equal to 1.33. You're trying to figure out, I guess this one's m for these purposes. You're trying to figure out the value of m based on this one. So divide this, yeah, 1.33. Divide this, 1.33.
Correct.
Question is, what do you raise 1.33 to get 1.33? The answer is 1, 1.
Oh, okay.
Yes, that's it. You won't see orders like, you won't see non-whole number orders.
Okay.
They're not common. And once in a while, I mean, I've seen some calculations where you get, and this is why I mentioned the log one, where you get like a 1.5, but that's not common. It's just, you double the concentration, whatever, you get 1.5 concentration. But the most common thing you run into are whole numbers.
So I was just reading too much into it.
Yeah, you think you're right about it. Okay. Yes, I mean, it's simple math. It's just divide one by the other and then ask the question, what do you raise for the one by to get the second one? Yeah,
The
listen.
highest order is like 3, right?
Yeah, you might see a 3. Might. Those aren't super common either. Most of the time they're 1s and 2s. Yeah. But in answer to Ollie's question, what's the most complex? See, I wouldn't even consider an order of 3 complex because, like, if you double the concentration and the rate goes up by 8, what's the order? 3. If you guess 2 to the 3rd power, gives you 8. If you triple the concentration, it goes up by a factor of 27. That's the order is 3 because 3 cubed is 27.
We've never seen like a order 4.
I don't think I've ever seen a problem with 4. 1s and 2s and 3s, those show up. 3's less common. Like,
So when they figure this out, I doubt that it's always a simple doubling of rate or whatever. Like when they're figuring this out, is it like, oh, the rate went up by 1 service or whatever? It's
Yeah.
the math to figure that out. And then, yes.
yeah.
Okay. So it seems simplistic, but easier that way. And I was wondering if it's always that way or if that's just.
You can solve it the same way. Like I say, the only reason I bring up the logarithms is if for whatever reason it doesn't show up quite so simple. One of the book examples gives you a 2.25 equals 1.5 to the end. Can you see that one?
Never calculate.
What's 15 squared?
265.
225. So 15 squared is 225, 1.5 squared, 2.25. But if you can't do that in your head, or you can't see it, that's why I mentioned if you go log of 2.25 equals n log of 1.5, n equals 2. It'll work. And if you really didn't like logarithms, you could do natural log. And that'll work too. I think your book gives you it goes natural log. I'm like, okay. I suppose you can do natural log, you can do regular logs, or I don't know, you can see the 15 squared 225 and that's a 2. They all give you the same answer. Alright. Let's go back here. Yeah, Angela.
Was it asked about the rate order as well as overall rate? You determine that the overall rate.
Alright, so you would be asked, let me go to this one. It's got so there's your rate log. What's the overall order for that particular rate log? 2. Just add up the exponents. So here, you say overall the rate was 2. You'd say it's first order ammonium, first order nitrite, overall order is 2. Solve for K using the rate data, you get K equals that number with proper units. So then here's the follow-up question for Holly. So what's the rate when those two concentrations are used? So could you solve that? Did anybody struggle with that? Okay, and if you would struggle with it, here's my comment to you. We're trying to solve the rate. You have the value for K right there. And I've given you concentrations. All that you need to do then is say rate equals 3.7 times 10 to the negative 4. Put in your units, molarity -1, sex -1. I'll put the first power in 0.438.
Can you just like the time?
Pardon? And then what cancels? One of the molarities canceled out to the side. And then it's just a matter of multiplying. And you should end up with a rate equal to 4 points. There you go.
I thought you were hard. Oh, wait, no, fair enough.
Yeah, they have to be
I looked at the first rate, the 10.8, it's going to be -7 instead of 2.7.
Okay. Yeah, remember that the K, and the K is going to be the same. So once you know the value for K in this rate law, you can ask the question, you know, what concentrations do you need to get a better rate? Do you want it to go faster? Is it all increasing? Is there a maximum rate? So, okay. All right, let's see what I got next. Answered all this stuff. Answered all that. There it is. Okay. Do you want me to go back through all of those slides? Because it's everything that I just walked you through.
No.
Okay, so if you watch very slowly, I'll at least go slowly. So there are your data. Compare 1 and 2. This one's got 5 and 6. Rates are proportional. That means the value of your exponents is 1. So there's your rate law. You have K is a constant. There's the order with respect to each reactant. Overall order is 2. Calculate K by picking one data set. And there's your answer. All right. Couple quick questions. A, B, C, or D? Is 2 true? Okay. About 3. About number 4. Okay, so the mechanism would describe which things react with which in which way. And that actually comes up later in the chapter. Number 4 does not. How about the stoichiometry? If you think back to the data that was up there, I never talked about the coefficients between reactants. So the answer is skip number 1 on intention. Okay. How about that? Back.
I don't know if this is okay, so like let's say that you have like an experiment and then your two reactants. What if one of them's like the limiting reactant and then you like, so then wouldn't that possibly mess up your ratio?
Not in terms of the rate. I mean, because just once the reaction, or once one of the reactants is used up, reaction stops. So your rate goes to 0. But you're looking at just initially, so you mix the two things together, you measure the rate right at the beginning.
Okay.
That's it.
Okay, so before that has a chance to happen.
Right. How about this one? Does the rate constant have the same units as the rate?
No.
Okay. And rate laws up there for part A. What's the reaction? What are the reaction orders? How would you describe them? So you're looking at orders of 2 and 1. So what's the answer? A, B, C, or D?
D.
So part B, does doubling the concentration of nitrogen monoxide have the same effect as doubling the concentration of H2?
No.
You should say no.
This is B.
Right? If the rate constant is 0, what's the rate?
0.
0, because its rate is equal to the rate constant times the concentration. So if K is 0, then there's no reaction. And let me see what I got. We did that one. All right. So I'm gonna say take a quick break. I'm gonna leave this one here. Right there. And then I don't know, like 5 minutes, and come back and have you run through a problem. Figure something out.